Okay,
Wonderful.
thank you for the opportunity to share the work today. And we will start with this very long title. And it has many, many words, so I hope that I make it clear and in a quite fast way. Okay, so first we start with entanglement and with the matter. So here it is a huge zoo. And I start with this very nice work from John Bell because it's linked with the props that we try to speak about for some years. So we ask, what if we probe half of a sample and we measure the charge fluctuations? So if we have a metal, we should find that the charge fluctuation at finite temperature behave as a volume of this subregion, temperature, and the compressibility. Now we may ask, what if we go to the quantum limit and T goes to 0? So if you take just a piece of wire, a piece of metal, and you apply a side gate, and you would measure the capacitance or the charge noise. What do we see? For this subregion A, we should find that the fluctuation that we call from our side f of A would scale at 0 temperature as the log of this length of the gate. And we can show that, in fact, it's linked with entanglement measure in a very nice way. And for free fermion, it measures the entropy for the Luttinger liquid or spin chain. And for metal, it similarly measures the correlations because it scales as the Luttinger parameter. And therefore, it's linked with the compressibility. Now, for free fermion, we can go beyond and, in fact, write a link between this entropy and all the charge accumulates. So it is a very nice probe in a way. Now you could tell me, okay, we spin. So we will speak about spin. So if you start with one spin and you couple it to a bath, it may be the quantum model or the spin boson model, then this entanglement, so-called entropy, is then some simple way to speak about spin observable in a way, and it reveals the phase transition of this known model. Now we ask, we take a 1D spin chain. What do we learn? Where do we have quantum? Where do we have temperature? So if you take a spin chain and you would measure this fluctuation, so you can do it if you would apply some field, but now we just have a field on one subregion. This could be done if you apply some screen that could be done through the Meissner effect, for instance. And then at large temperature, if you just measure the fluctuation of spin measure, then you find that at large temperature, it scales like the Curie factor. It's like each impurity, each side would be like some local moment. And now at low temperature, you see the quantum behavior from this fluctuation because the correlation start to bring some log behavior. First, log of temperature, and at low temperature, it scales again at log of length. So here, length would mean the perimeter of the screening superconductor. Then you may ask, okay, what if now we have couple chains, and then we have some ladder, and in this ladder we may have some dimer, some Bell state that are formed on each rung. So if you take one ladder and you have bell pair on each rung, and now you cut in the middle of each bond. We should measure for one ladder, or for that the fluctuation should simply scale as the number of link that we cross. So if we have L link, then this fluctuation should scale as L. Now, if you go in 2 dimensions, and we have the null phase, the 0-point fluctuation, give fluctuation, now that scale in L log N. So from this probe, you could maybe see, some things about how we can probe a valence bond state, or some Bell state, and some null state with a spin wave fluctuation. And I should say that the log behavior just for the 1D wire or the quantum point contact is yet to be seen. It's not yet seen. Then now what I plan to do is simply to zoom on one rung or a few rungs, and ask how we can really propose now some ways to link this entanglement measure with some simple topological numbers. So to do so, we take, say, we start with 1 or 2 spins, and on each side we are on a Bloch sphere, and we form one skyrmion, which means that you may apply some drive if you have artificial atom, for instance. But if you have the material, this means that we have real model linked to this skyrmion. So we start with, say, 1 spin. We have 1 skyrmion because we have the D vector that form a sunny shape that way. And this implies that if we just have 1 spin, then we would measure 1 topological charge, or a so-called magnetic charge linked with this skyrmion. You can similarly measure this charge from the Berry curvature, or simply from the pole, through spin observables and through the Berry gauge potential itself. So if we just start with one spin, of course, we would here, because we have this radial field, we would measure just 1 C number being equal to 1, and which mean we have 1 skyrmion. Now we ask, what if we start with 2 sides or a rung, and we have 2 skyrmions that start to interact. So to do this, we act with the parameter R. And you see that it's some spin interaction R here, which couple a rung in Z direction. So at the same time, we add the MI parameter, which would favor the charge to leak out from each sphere, and ask, what if M is smaller than D? So we have 1 skyrmion on each spin, but now they interact through R. So first, you can show that if R is large, this would make a phase with the C number being 0 on each sphere, which means simply that the charge yes, so the charges are out. And now the new point that we want to make is, if now you fix R between D so-called minus M and D plus M, you find a new phase where at North Pole you see the spin simply follows the field in red. So you have some nice state, But now, if you change the polar angle, you see that close to theta equal pi, things are different. You find a bell pair. And so it's like each sphere would swallow the spin. So now the fact is, if you try to measure the Berry curvature so here the key point is we have an inversion between the two spins. So which means that the D vector are equal and M1 equal M2 equal M. So then if you measure the Berry curvature, you find that the flux on the surface is half of a skyrmion. And therefore, it's like a 1/2 flux quantum, but in a sense, because of this pair circular formation, but in a sense of somehow the Berry functions. So what we say then is you can really measure the fact that you have one pair at one pole from this new C equal half number. You can see them if you drive in time from North Pole to South, and you can similarly measure the bipartite fluctuation on one spin. So you simply measure the variance of one spin and shows that it would mean CJ equal 1/2 for each spin. Now, if you add an interaction in plane, it helps to see this phase. So here it is a good news that we have a new phase simply that comes from simple spin model, and the fact that you apply this field that try to build some skyrmion, but at the same time you have the R parameter that try to create entanglement. So then here we show a very nice experiment from somehow from somehow Skolorushan et al., which should be here. And so they have built this two-spin model with the right fields, and they have an XY coupling, so they should see the bar here. That should mean the fractional phase, but for their experiments, they don't have the M field, which is H0 on two spin. So for them, the green band means that they have somehow C equal 1 on one sphere and 0 for second. Or yes, so they don't see yet this phase, but this yes, this they could. Then one thing that we like is you can similarly do very nice things on a sphere. You can really measure new function through light or through metrics. If you change the angle phi in the plane, then you find a beautiful line which is at the top when you have one skyrmion. Then it's linked with a quantum metric that has been measured in a circuit. And at the same time, this means a new function. These functions here that you can measure through light. So it's nice because it makes a close path between what we know about C number, about somehow quantumness through metric, and some new functions that you can measure with light. Then if you have two spheres, you can shine light. At North Pole, you would measure C equal 1, and at South Pole, you would measure C equal 1/2. So just from the pole, you can measure if you have the ferromagnetic state up, or the pair at South Pole. So what I try to say is from this tool, just with two spin, you can really reveal new feature of somehow how you can measure that we have entanglement linked with a new probe and new function. Okay, so now we ask how this can help us to see new light for planes. So then the thing is, you may think about two spins. So here we start with a rung of a ladder, but then we may ask, what if now we have a full ladder? So we will go back to this after. But first, we may ask, what if we have two planes? So if you have two planes, what we thought of is to build some simple model. So you have two planes, and in each plane we have one skyrmion. So which means that we have an all-day model. So this means that we have a dizzy term that we know very well, and we have a graphene plane through the functions called sigma x and y. Now the new feature that we want to add is the M term. So the M term could be done with a substrate, and for two plane, the R term means hopping. And here it flip the plane, so it means that you hop from A to A, blue bubble to blue, and B to B. And we can similarly think about this model in graphene, like in this work. And you can do the same. So for one plane, S would be the spin matrix, which simply means that you add a small field in plane. So you see, now we speak about a quite simple model. We start with a one layer graphene, and we add a substrate to have this M term. And we simply add in plane cyclomagnetic field. And what we found is, if you tune R between, so dizzy would be sort of as this term called T2 here. And if you tune R within this region, then you find some new phase. So now you have some band. You can show that they mean some edge mode. So if you look at the red band, it has some edge mode, and the spin point in X axis. But now you have two bands, red and blue. So red would mean down X, blue would mean up X, and now they cross the Fermi level at half filling. So which means that we have maybe some C number or Z2 number, because here you see a new cross, which is very similar to the one that we have for the quantum spinel effect. But now we have bulk modes, because this red band in the bulk crosses the Fermi level. So yet we have shown here in the group that you can really show the Z and the Z2 number with the same tools, and you can really detect the edge mode first through RPES. You could maybe see this band structure, and the fact that these modes are stable with interaction with impurities, with weak interaction, weak impurity. And we have new ways to probe this Z number linked to Z2 number at Fermi surface from a circularly polarized light. And at the edge, the blue mode give a perfectly quantized edge circular conductance here. Okay, so now how do we see that this is linked with two spheres and entanglement? So if you write each band which goes along x-axis into z-axis, so then we have and we zoom at k and at k point and the k prime point of graphene. Then if we are at k point, we find that the two-particle wave function is the same as on a sphere. So here we have to juggle with our mind and think that up and down mean sphere 1 and 2. And A and B mean then what was the spin before for the two-sphere model. So then if we do so, we have the same two-particle wave function as on a sphere. And now you see that you can nicely rewrite the wave function at k prime point as some entangled wave function. Then in fact, you can go on and write down some local marker at k end of the k prime point. That would mean the same C equal half than on the two-sphere model. And then you can really make a link between this and the light response. Then for the time being, what I will try to do now is to show application for Majorana fermion. So the fact that we have these two spheres is nice. When you have the formation of bell pair at one pole, you can write on this pair in terms of two somehow so-called Majorana fermions, alpha 1 and eta 2. And in this work, we showed very nicely that you can build some very nice qubit with this pair. And the good news is, a priori, it is nicely stable with the mass if you would deform the mass with small somehow circular disorder. Then if you would couple to noise, we have shown very nicely that this is stable too. Because why? Simply because for this new spin, one operator, tau y, would be some non-local function. It's a sigma 2x, sigma 1y, which would not really couple to okay.
Karyn?
Yes.
If you want to leave like a few minutes for questions, you might want to start to wrap up.
Okay, so then what I have to say is that we have new linked with the wires. We have new ways to link with the p-wave wire, and new phase for two wire. We get a beautiful, nice DCI phase that link similarly with the fractional number and with the Majorana fermion at one pole on a sphere. So here it is a new phase with interaction where we have really developed new tools with the DMRG to apply the information from the pole into the wire. So here it is a very long road, but it is a very nice work that we have done here at CPHT in particular, where we have shown now that with interaction you can reach this new phase of matter. So then if you would ask me for more spins, we have a new way to think about fractional numbers. And I will try to give my view on cuprate, because I think if you would ask me what would I believe right now, it is very complicated. If I show the phase diagram of the cuprates, and I would take the view of the green function. We know well what it should be into the D wave dome. We should know what it is at half filling from mod state, but then it is not simple to see what would happen for the pseudogap phase. Then I could ask, okay, if I take the bipartite fluctuation, I obtain the purple answer. So we know well what should happen for all the phases, superconductor, mode phase, and Fermi liquid. But we don't know yet how to link the green function of the pseudogap phase with transport, with a very nice transport experiment. It's not simple. And one fact is, if you take the entropy of the Cooper pair, you could yet somehow see it with RPES. Because if you take one Cooper pair on a Fermi surface, you can show that it is a very nice and a simple function linked with the gap information if you are in a blue dome. So I think that I will then somehow conclude with this very large puzzle to me, because there are somehow many ways to think about the same thing, and yet it is not so clear the link between all of these probes. So thank you very much for your information, for your attention, and I will take the questions. Thank you.
Wonderful. Thank you, Karyn. We have 2 minutes for questions. Are there any questions? Yeah, Timio would like to ask something.
Thank you for connecting. I had a question about bipartite fluctuations that you mentioned. Is there some effort to implement that from an experimental protocol?
Yes, yes. So it is a good point. How should we do to see it? So if you take a quantum point contact, so which is this, here you have a blue piece, which is a metal, you have some probe R. What we have shown is if at time 0, say, you close this, the bridge, and now at time t, you somehow open it. If you have a perfect channel, you should see that if you measure the charge noise linked to the charges that go through, you should see in time log t. And in fact, it is log t time d, where d means how you somehow couple the particle on left and whole to right. And so this should be done, because this seems okay. The time you need should be fine. Then if you ask me why not take in one wire and you apply some gate. The gate would be capacitively coupled to the wire. So from this, they know well how to measure the charge on a dot. So they should see the charge on one region of a wire. And then here, the new point, they should measure the charge noise. And to see how this would scale if you change the length of the gate. And it is the same thing for spin. I try to show that for spin, you could have a Meissner screen. And now the point is you should change the size of this screen and measure the same the spin variance on one region. So here, this sounds maybe okay to me. Somehow, yes. Thank you. Yes.
Any quick questions before we move on to our next speaker? Okay, now let's thank Karyn again for this great participation.
Thank you. Yes.